All right. So if anybody, has any value of going back and looking at these,
Will you post these recordings on Canvas or something?
Yeah, I'll post them. Let me think it through whether I should do it on YouTube or Canvas or Zoom or whatever. But yeah, I'll post them.
Yeah, so I just wanted to ask that and introduce myself.
Okay. Well, welcome.
All right. Thank you.
All right. Anybody else want to go next?
I like to go next.
Okay, Kevin.
Hello. I just have a small question on apps. It's because some labs have certain items that we don't have at home. I was wondering how are we gonna record data?
Oh, well, the answer is the same for all my classes, but let me just ask you what class you're in.
I'm in your 102, I think.
102? Okay. Right. So you haven't done a lab yet this week, but no. You will next week. And you're right. The most challenging the most challenging part of this course, I think, is trying to make the labs successful. And here's what I'm going to do. You'll see me explain this in the first lab video. I made it a little while ago, and I'm ready to send it to you on Sunday night. And what it is you and me will be partners. Okay? So I'll actually be in the lab. I'll turn on the video camera, and I'll say, here's the lab, you and me, and I'll go over and I'll get the equipment and I'll put it on the table, and you'll kind of watch me do that. And I'll actually, run the experiment. And then I'll say, okay, write down this number. And I'll say, okay, here it is. And there's a length to it. And I'll say, all right, what's that length? Write it down.
Okay, so essentially we'll be recording mostly your data.
Yeah. So I'm going to, it's not too much different than if you were actually in the lab. If you were actually in the lab, you would be working with a partner, and one partner would write down the numbers as the other partner did it. Of course, you would rotate in a regular setting, and in this case, we can't do that. So I will be everybody's lab partner. I will be the one always setting up the equipment, and you then will watch it and write it down. And like I said, my first video on the first lab, I'll take about the first 15 minutes and explain this in detail. And you will then take, I believe the first lab is a total of 5 pages. And you should have the lab manual with the welcome email I sent you.
Yes, I also have the physical copy.
Good. Oh, and it's probably useful to have a physical copy or a printer, because you're going to, write these numbers on a table. You could use technology. Some people can write on their screen and whatnot. So whatever is easier for students, I don't really care, but you're going to have your table, and as I make the measurements, you got to fill them in, and then there's places for you to do some calculations, so you got to calculate, and there's a place for you to answer questions, and then and graphs are big. The lab manual comes with graph paper, and so you'll do 3 or 4. I think this first lab you do 3 graphs, and we'll study those graphs to answer the questions. I believe there's 9 questions on the first one. Ultimately, then it breaks down this way: that the 3 parts of the lab, the first part, collecting the data, we do together. I and you do together at the video. Then you either on your phone,
The first part is like in a Zoom live, or?
It's not Zoomed live, no.
Oh.
It's recorded. Okay. So you, which has advantage and disadvantages. I'm not live, but you can also rewind it and pause it and look closer. Yeah. But the big thing is our school wanted you guys to have the freedom to be able to do the lab at time of your choosing. So if I send out the video on Sunday night or Monday morning, you could do it on Monday or Tuesday or Wednesday or Thursday, Friday or Saturday, and then it's due on Sunday. So you pick
Okay.
the day and the time.
So this Sunday you'll be setting up the video and then posting it on YouTube?
Yes.
Okay.
And so you watch it. That's the first 1/3 of the lab, collecting the data. And then you'll see that you have to analyze the data. And that means you have to make the graphs and do some calculations. Then there'll be 9 questions that you have to answer. And so go ahead and do those 9 questions. And then when you're all done, you'll scan or take a picture of those 5 pages and then load them up onto Canvas. And by that time, I will have activated Canvas so you can turn it in.
Okay.
So good question about the lab, but I'll also let you know that I purposely have not explained anything about the labs because that's coming. That's coming for week 2.
Okay. Thank you so much
For you guys in the 102. You guys in the 122, remember, we're in the middle of the book. You already did your first lab, or you're doing it. So I made that video on Monday and sent it to all you guys in 122. And you can go to your Canvas page right now if you already did it and turned it in. But again, it's due at the end of the week, so Sunday night for you guys in 122. All right. Anybody else want to go? Have a question for me? Either about the logistics of the class or maybe another problem one.
What's testing going to look like?
Oh, yeah, great question. Testing, I'm going to upload the test onto Canvas, and then there'll be a window, and depends which class you're in. Anthony, you're in 122?
Yeah.
Okay, so your class is 2 hours long.
Mm-hmm.
And the traditional time is, I can't remember the traditional time, but I'll set that 2 hour window at the traditional time. And if that doesn't work for you, let me know and I'll give you another 2 hour window. But for most people, I'm hoping that 2 hour window will be, excuse me, it's a 2 hour window to take the class, and then it's another 15 minutes for you to scan it and upload it. Okay.
Okay. So it's.
But you're going to take it the traditional way. You're going to write it on pencil and paper. Other than you'll see the test on your Canvas screen, and for you guys, it's a lot like your homework. There'll be a question.
You have to submit answers and then submit work on 2 separate assignments. Okay.
Yeah, so you'll just get a piece of paper and write down, okay, solution to number 1, and then just begin. And you should, well, I shouldn't say you should because it doesn't really matter, but it'll probably fit on 1 page. And so
Yeah.
you just got to scan the 1 page and turn it in.
Will the computer be detecting our answers?
No.
No, okay. So you're going to do all the grading. There's not going to be any, because
Right,
in the engineering class, there's a graded assignments that we do, but you have to round in a very specific way or you get docked points and you won't be giving them back. So
yeah, what program is that?
Engineering 115 statics. So.
Yeah, I have not been a fan of those computer inputting technology. I feel like students get cheated a little bit just because they didn't follow the strict protocols of the program, and that's not what I want to see. I want to see your work. I can tell from your work what your thinking is, and I feel like I can evaluate it much better when I just see pencil and paper work. And when I've tried those programs in the past, I wasn't happy and the students weren't happy
Mhm.
So, because I tried those with the homework, I thinking, hey, here's a young generation. They're into technology. They'll like this. And no, they did not. They just preferred to do it the old way. And I do still think the old way is the better way, where you just write it out. The only exception to that is, some of these, like the iPad Pro and Microsoft has another one, their workbook or but anyways, they're really good to write on the screen, but you're still just writing. So anyways, yeah. So I hope you like that better, because that's my approach. I think you should just write it out and scan it and send it to me, and I'll just call it up on my screen and grade it like it was just a regular piece of paper.
Right. Okay. Will the test questions be to the same caliber that the homework ones are?
Yes, the test does this. There'll be 5 questions, and they go from easy to hard. So,
Okay.
the first one, you'll look at it and go, well, this is easier than the homework.
Right.
And the last one, you'll look at it and go, oh, that's harder than the homework.
Exciting.
So, well, I shouldn't say that, because, and you can't see this because the homework is scanned in black and white, but the homework problems are color coded. Black for easy, blue for medium, and magenta for the hard ones. And the real hard magenta homework problems are way too long to put on a test. Way too.
Oh,
Yeah.
okay.
So I like to say that the test starts with some black problems and then finishes with some blue problems, but it doesn't go to the magenta. There's just no way. There's some of these problems there's no way you can do in 2 hours. I mean,
Yeah.
for your class, you got to be on an average pace of 25 minutes per problem.
Mm-hmm.
And so hopefully problem 1 goes a little faster than that, because you can use that extra time for the harder one on number 5.
Right. Okay.
Let me see. I got some questions here in the chat. Had a question on the lab. I'll shoot you an email instead. Okay, thanks, Gina. Hi, can we do number 16? Sure. That was Claire, right?
Not me.
Oh, but not that Claire. Is there another Claire in here?
I think it's Clara. Yeah.
Oh, Clara, thank you. My bad. Oh, there's Clara. I see. Clara, are you? Oh, but my microphone doesn't work. Sorry. Okay. So I take it you can hear me. Great. I will do number 16. Sure. Clara, I guess I could see by the homework, was this a question from the 102 class or the 122 class? 102 or 122? In fact, let me just look. 16. Now, there is a 16 in the 102. It asks for what is the typical mass of a 5'6" female. Let me jump back up to Zoom, because you probably answered
I think
me.
she just said 122 was her
Oh,
class.
thank you. 122. All right. So let me change the homework from 102 to 122. All right. Number 16. So this says, if a 2 microcoulomb charged particle is located on the x-axis, 2 of them, sorry, one at x equals 1 meter and the other at x equal -1 meter, determine the electric field on the y-axis at y equaling a half a meter. Okay, so it's an electric field question. Good. And maybe the best way to do that is for me to share my screen again. Okay. See if I can do this here. Okay. Share, iPhone, share, and then it's going to ask to Do a video share. Okay. Nice. Okay, I think that's connecting. And I'll just write on my piece of paper number 16. Number 16, chapter 23. Okay, good. All right, so let me start with a little picture. So here's a grid. In fact, let me go back on my other screen to zoom to see what you guys are seeing, see if it's coming through. Oh, good. Looks like it's coming through. Everybody good? Okay. And then the two charges, one of them was at a position of -1, and the other one was a position at +1. And now I need to go back to the question. Let's see. That's not the question. 16. So what was the charge on this? 16. There it is. So, so this has a 2 microcoulombs, and the other one was also a 2 microcoulombs. So it says two microcoulomb charged particles are located on the x-axis. And they're saying determine the electric field right here. Now, I guess I didn't draw that very good to scale because they're saying this is only a ½ meter up. And so find the electric field when it is at a ½ meter. Okay. So here's kind of the magical piece of this. And this positive charge would make an electric field going this way. And this positive charge would make an electric field going this way. And so, Clara, I hope what you got out of the reading here in 23 is a lot like in physics 121, we have to add a bunch of vectors together. The total electric field is, and I'll just say electric field number 1, and over here I'll say electric field number 2. We have to add the 2 electric fields together. And so in 121, we did stuff like this. We were adding forces, though. We weren't doing electric field. In fact, let me switch my screen back so I can see a chat. If you want to say anything, Claire, go ahead. Clara, go ahead and shoot a message to the text box here. Okay. But I'll keep going like it's making sense to you until you stop me. And so as I look at these 2 vectors, and I look at their component, both of them are up, but one of them is sideways to the right, and the other one is sideways to the left. And let me give you a very, very helpful hint here. Look for symmetries or patterns as you do these problems, because one thing I see right away is that when I add these 2 together, this one, which is up and right, and this one, which is up and left, the left part of this one and the right part of this one are equal and opposite. So they're going to cancel off. So since the total has an x component plus a y component, I can probably save myself a lot of work and a lot of time during the exam. That's the key. By noticing right away that I really don't have to do anything for the x component. In other words, the total electric field in the x direction is 0. And so that's a huge advantage. I don't have to worry about the x component. And in fact, look at the y component. So the total electric field in the y direction is really going to be twice the electric field in the y direction from just one of the charges. So coming back up to the picture here, notice that they both have the same vertical component. So if I just find the vertical component of one of them and then double it, I will get the total. So I'm very glad you asked this, and I hope what I can get across, is when you have problems like this, look carefully for patterns of symmetry and save yourself a lot of math. If you do half of these problems with the physics, then the other half by math, the other half is really easy. In other words, instead of me having to do both x and y, which is a long problem, I only have to do y one time and then double it. And so I would say, noticing that, I only have to do 1/4 of the amount of work that I first thought. I first thought, okay, I have to do an x and a y component for this one, and x and a y component for that one. And that's 4 pieces. But as I look carefully at it, I see that the x's cancel off, so I don't have to do those. So 2 of those 4 go away. And then I don't even have to do both of the y components. I only have to do one. And so that's what I'm trying to emphasize here, is that there is ways that if you're thinking about the physics, you're doing more than just plug and chug mathematics. You can make this a little easier on yourself. Okay, so now I will finish the problem by then saying 2 times. And so to get the electric field in this direction, let's move it down. I'm going to call this angle theta, because this would be then the magnitude of the electric field. And since I want the y components, I got to take the cosine of that angle theta. So there's the 2. Now, how do we calculate the electric field from a point? Well, that is Coulomb's constant times the charge, which in our case will be that 2 microcoulombs real soon, divided by the distance between them squared. And then, of course, this cosine theta. So I'm about to finish this problem, but to do that, let me come back up to my drawing, because I'll start with the distance away. So this is the distance away. My drawing doesn't show it, but this is supposed to be a distance of 1 meter, and this is supposed to be a height of 1/2 meter. So if I do Pythagorean's theorem here, it would say 1 squared plus 1/2 squared equals the r squared. So this is the r right there. And so if you square 1, you get 1. If you square 1/2, you get 1/4. And so this is 1 1/4 equals to r squared. And I'll probably also need r. So let me grab my calculator and take the square root of 1.25 and get 1.12. So 1.12. So there's the r. Now also, of course, another thing I need to plug this in is the theta. And so what I'm going to do is first do a little geometry. This is the angle theta, but if you remember from your geometry, vertical angles are equal. So that means this is also theta. So tangent of theta would be opposite of 1 over adjacent, 0.5. And so that's a 2. So I can get, oops, it's off the screen there, sorry about that. So the tangent of theta, which is equal to 2, will allow me to grab my calculator and go inverse tangent, there we go. Inverse tangent of 2 is an angle of 63.4 degrees. So 63.4 degrees. Okay, so now I can come back and then actually put in the numbers. 2. Coulomb's constant is 9 times 10 to the 9th. And if you remember from the reading here or the lecture, the units for a Coulomb constant are newtons over, times a meter squared, almost forgot that, over a Coulomb squared. So there's Coulomb's constant. The charge, let's see, back up here in the picture, was the 2 and microcoulombs. And so I'll just remind you back to, I guess it's 121, chapter 1. For that matter, it's also for you 102 people, but the first chapter has the prefixes of the metric system. And so the micro means 1 millionth. So that's the charge, 1 millionth. Then I have cosine of the 63.4 degrees that we just calculated, looking at the picture there. And then all of this is divided by r squared, which we figured r squared earlier as 1.25. 1.25. And that's actually square meters, because I didn't put it in here, but this would be a meter squared and a half a meter squared. So it's meters squared, which is great because when I start canceling units here, this meters squared would cancel with that one. And one of these coulombs would cancel with one down there. And I'm left with newtons per coulomb, which is the appropriate units for the electric field. And now I can just grab my calculator here and start inputting this. So 2 times 9 times 10 to the 9th times 2 times 10 to the negative 6 times cosine of 63.4 degrees divided by 1.25 gives me a number of 12,000. And maybe I should be a little careful with my significant figures. So maybe I'll do 3 significant figures. And there it is. And it's only in the y direction. So to write it as a vector, I will put that. Yay. And Claire, I didn't see any questions for you, so hopefully you were following along. And just out of my own curiosity, I have the solutions somewhere. Let me look on my other screen. There it is. Yep. They write it this way, though. They write it as 1.29 times 10 to the 4th. Yeah, okay. Same thing. Newtons per coulomb in the y direction. Cool. And I see here the answers. Oh, my bad. I didn't quite finish because there's a part B. And so part B then is the easier of the two. In fact, let me use this as a rough comment to those of you in 122 who might be struggling. Remember, the key is to really find the electric field. In fact, I'm going to draw this, a little diagram that you saw in the video lecture. The goal of this first chapter is to say, what is the electric field from something we know, like say a point, and then you can find it with 2 points, as we're doing in this problem, by adding those two together, or a bunch of points and you can make a ring or a rod, or a bunch of rings and make a disc, or a bunch of discs and make a cylinder. But that gets you to the electric field. Then the easier step is the part B of this problem, is to say once you get the electric field, you can get the force. And you do that by saying the force then would be the charge you put in the presence of that electric field. Now I'll come back to part one here in a second, but I want to finish this diagram because then we can start using our physics 121. If we know force, we can get acceleration. And if we know acceleration, we can get velocity. And if we know velocity, we can get position. And so all of this, all of this is what physics 121 was trying to teach you all about the mechanics. And then what I'm trying to add to that for this chapter is this, that you can get the force. And this step is the easier of the two. This is the hard thing. This is the one that 90% of the struggle on the homework is all about. But let me show you this last step, and I'll bring the picture back. So what they're saying in this problem is right here, we have just found that electric field. And now we are going to put a charge. And they say put a -3 microcoulomb charge at this location. And just to kind of interpret what we already solved for, we already solved right here that the electric field at that location is about 12,900 in the positive direction. So I come back here and draw a picture of this. This would be saying the total electric field is pointing straight up. It's only in the vertical direction, and it's got a value of 12,900 newtons per coulomb. And again, conceptually, we know that if you put a charge in that field, it is that field that pushes on it. So you put a charge here, there's going to be a push. And the push is in the same direction of the field for a positive charge, but it's in the opposite direction for a negative. So we would expect the force to be in that direction, the negative direction, because again, we're putting a negative in here. Okay, so let me finish up part B by saying, okay, so here I'm going to put a -3 microcoulombs of charge where this field is, which the field is 12,900 newtons per coulomb in the y direction. So when I multiply this, so -3 times 10 to the -6 times 12,900, I get a value of -0.038, coulombs cancel off, and we're just left with newtons and the j hat. So we've got a force in the negative vertical direction as predicted. And let me just come back to the answer, see if I'm still on targets. Struggling my computer. 3 times 10 to the -6. Yeah, good. So, right. So back to the Zoom session. Yes, perfect. Thank you. I see. Thank you, Dr. Young. So Clara and Clara both are, I think, good. I don't, good. Looks like Clara took off. Good. She said she didn't need any questions. And all right. So I see when.
Hey, Professor.
Yeah.
I'm in your 102 class. Are you finished answering that question so I can ask you a few?
Yeah, maybe I should. Well, to be a little fair, let's see. Can you shoot it into the chat room so that because there was one in front of you here.
Okay.
Yeah.
I just have some conceptual questions, so mine will be quick, but yeah, I'll put them in the chat.
Oh. Wait. Hang on, Daniel. Maybe yours would be quick.
Yeah.
Yeah.
I can't.
Thank you. Yeah. Okay. Go ahead, Daniel.
Okay, cool. So I just have a few questions. Number 24 on the 102 homework.
Okay.
I can just say it really quick. It's about a rock being dropped into a mine shaft.
Oh, yeah.
Yeah, so it's just a conceptual one because I did a Pisces tutor yesterday and she kind of confused me a little bit more than helped me.
Okay.
So I know that acceleration is constant with gravity unless there is like resistance, particle resistance. So I'm not sure how we're supposed to be able to figure that out when we don't, because all we know is that it's heard 4 seconds later.
Right. Okay. So let me, the conceptual part of this, and I'm going to put a piece of paper right here that I kind of worked it out. I could start again from scratch, but even before you look at that piece of paper, let me just do the conceptual. The conceptual is this, or maybe you should look at the piece of paper because I'm going to point to it. We have an object starting some height above water, and it's going to fall for 4 seconds. So they're asking how deep the well is. Great. But the follow-up on that is really saying, how far would a rock fall after 4 seconds? And I can't tell by the expression on your face if you made that clear.
Okay. Yeah.
That's
We're
the
asking how far it would fall, basically.
Well,
Yeah.
right, but you got to figure that out. See, they said
Right. So do we need to have like the constant for acceleration? Do we need to just like look that up?
Okay, good. Well, I wouldn't say look it up because you should be memorizing this.
Is this
See,
for 122?
102.
Oh, okay.
So for a anytime something is dropped, okay, and so again, this is a little bit ahead of our lecture. This is chapter 2. So I don't know if you've gone ahead and seen all of the videos from chapter 2. I only forwarded out the first half of the
Right.
chapter.
I only watched the first half of lecture 2, so maybe that's why I'm confused.
Yeah, it probably is because you're ahead of the game here. When you watch the rest of it,
Then it will be clear.
yeah. In fact, I even do a problem exactly like this.
Okay. Then I just have one other quick one. It says a hard rubber ball is bounced on the floor. My question is, it says compare the acceleration. It's 51. Compare the acceleration on the way down to acceleration on the way up.
Oh, okay.
How are we supposed to know how bouncy the ball is? Does that
Okay.
matter?
No, it doesn't matter. No, it doesn't matter. That's why it's a great question, because that's where students' thoughts will go. And let me answer it, but I'll also start off by saying, again, when you watch the second half of chapter 2, I think this will make a lot more sense.
Because the first half of the homework I was fine. Everything is easy from there. So
See, at this point, you should have only done chapter 1.
Okay.
Yeah. So if you did chapter 1, you're on target.
All right, cool. Because I noticed that it said though that week 1 it was chapter 1 and 2, but is that the summer schedule maybe?
Well, it's more. I guess I should phrase it a little better. It's do everything from chapter 1 and only half of chapter 2.
Okay.
See, next week we'll do the other half of chapter 2 and all of chapter 3.
I see.
But the short answer to yours then, before I lose you and go to a harder 122 one, is to say that what you'll see in that video lecture is the acceleration, whether it's going down or up. Now, not bouncing, not when it's actually in contact with the ground. So that's why that question is important. They're not talking about while the ball is in contact with the ground. But while the ball is falling or while the ball is rising, you will always get the same acceleration of that famous 9.8.
Right.
And it doesn't matter how big the ball is. This could be a basketball or this could be a baseball. It doesn't matter what color it is. This could be an orange golf ball or a white golf ball. It doesn't matter what day it is. This could be Tuesday or Wednesday. And so the thing that I was saying you should memorize is just memorize the acceleration when something is free falling is 9.8, which we'll kind of round to 10. And it always is that.
All right.
Yeah.
All right.
Okay.
Thank you so much.
All right. Keep working. You're doing great.
Thank you.
All right, let's see. Yeah. What was the question? Help me out. I need to learn how to pronounce your name. Hi.
Let's see.
How can I pronounce your name?
Timmy?
Kimi?
Yes.
All right. Thank you. You think I would know it by now, so forgive me.
Yeah. So just
But I guess
problem 20, and I don't
Okay.
get why direction is negative. Maybe
Okay.
because I draw the diagram wrong.
Problem 20. Why is it negative? Well, let me start by going back to the Physics 122 homework. And number 20. Oh, okay. I have a feeling that okay. Okay. Yeah. Okay. This might be better if I show you on my camera. Is my camera still sharing? Oh, good. My camera's still sharing with you. Okay. And so number 20 in class 122. I guess this is chapter 23.
Yes.
And it sounds like you'll be okay if I jump all the way to the answer. And so
Yes.
they do this. I better draw a picture. Let me go back to the question so I can draw a picture, because it says here that if you have this grid, okay, and this grid has a continuous line from here to here. And they calculate, so this is distance x naught, and it goes out to infinity. So your question wasn't anything about solving it. So I'm going to assume that you're good with the answer that comes out to be the electric field equals, and they have Coulomb's constants, E, times lambda naught over x naught at first. Okay.
Mm-hmm.
But what they really meant by this, and this is the key, is they were calculating magnitudes. During the derivation of this, they said that a small amount of an electric field comes from a small amount of charge and a distance away. And they actually treated it at first as a magnitude. See, watch this picture. Watch this for a second. If this rod was positive in charge, then all of these positives would make little tiny electric fields in the negative direction. So this derivation was not trying to come up with what direction it is as much as what magnitude it is.
Yeah.
Okay? Now watch this. If this rod had been a bunch of negatives, the electric field would have gone in the positive direction. So the way your author does this, and I think this is finally getting to your question, is your author says, we can write this as a vector by doing the following. First, write the equation for the magnitude. Second, put in the vector for what direction it is, I hat or j hat. And then now finally to your question. If you look at this, and I'll come back up to the picture, if you put in a positive for the charge density, you're supposed to get a negative direction. If you put in a negative for the charge, you're supposed to get a positive direction. So in other words, the direction of the field is opposite of the sign of the charge. Opposite means negative. So they
You said if I get a positive charge, I'll get a negative direction.
yeah, let me come back to the picture. So if this rod right here is positive,
Yes.
it'll go that way.
Yeah.
Right. So I like to write it this way. This, to me, is a better way of writing it. Because this tells me the direction of the electric field is opposite of the sign of the charge I am using. So if I use positives, I get a negative direction. And I think you see it now. You're shaking your head.
Yeah. Thank you. Oh, actually, if there's no more question, I would like to ask 22 as well. It's
Okay.
kind of more like an extent of 20.
Okay. I don't see anyone. I certainly don't see anything in the chat here. Okay, so let's go to, let me go back here. You said 22 was an extension of that one? Oh, yeah.
Yes.
Well, kind of. This is a ring, isn't it? Yeah.
Oh yeah.
Yeah. I'll gladly do it, but I'm not sure I would describe it as a continuation. So
Is the electric field around the ring always the same equation? That equation you use for that problem, is it always that same equation for a ring?
I want to ask the same thing.
yes, but also I want to be a little careful with your vocabulary. And I'll draw a picture while I'm answering you. When I make a ring, the equation that you're referring to, and of course, before you went off to class, we were dealing with this one in the 8 o'clock one. You saw this, that the electric field from a ring, let's see if I can remember it, is Coulomb's constant times the charge of the ring times x, where x is the distance away from the center, and then an a squared, where a is the radius of the ring, plus the x squared over 3 halves. Okay. Now, Daniel, the only thing I wanted to add was be real careful here, because this equation is limited to the electric field along the axis of symmetry only. So this is a good equation, but if you solve in the derivation because of the symmetry, it's only valid along the axis of symmetry. So
Yeah.
when you said it's for a ring, I got a little concerned that you might have to somewhere else. This is only along the axis of symmetry.
Oh, yeah, but like it's like if a circle is centered at 0, 0,
yeah,
the formula is it's the basic formula without shifting.
Yeah.
Okay.
Yeah. So what we and by the way, maybe I made that too complicated, because if you were off center, this would be mathematically a lot harder. So we're not going to do that this semester. That would be your electricity calculations when you take this again as a upper division. So your junior year, when you transfer to a 4-year university, if you have to. I don't know what your major is, so you may not have to. If you're electrical engineering or physics or something, you'll have to take an upper division of this.
Okay, that answers. Yeah, sorry to jump in on that. I just
I'm sure that's good. Yeah. Okay.
You asked the question of the question that I was wondering about. So sorry.
Yeah. Good. No, that's probably the most efficient way of doing it. Okay, so now let me go back to answering this question number 22, and hopefully some math comes to your head, because in this problem number 22, the question says, where is the maximum of the field? And so the maximum is kind of a standard question you would get in a calculus class. What is the maximum of a function? And so what that triggers in my brain is take the function and take its derivative and set it equal to 0. Because that's how you find minimums and maximums. Now, I suppose we maybe even might want to give this a little thought about what this equation might look like. And if you look back here at the equation at x equals to 0, which would be the center of the ring, the electric field would be 0. You see that right here. And as you move away, the field increases, at least the numerator increases, but eventually the denominator takes over. So it would increase, reach some peak, and then eventually asymptotically approach the axis like that. So a function that looks like that has only one derivative equal to 0, and it is a maximum. We won't have to worry about minimums, and we won't have to worry about, you know, multiple solutions. There is only one maximum. So, okay, that's nice. So now let's actually then do the calculus and take its derivative. So the derivative with respect to x of this thing. So here's Coulomb constant times Q. Here's X. And I think I've showed you this trick before in the workshop. Your call. But when I take derivatives, I'm never a big fan of the quotient rule. So anytime I have a quotient, I turn it into a product with a negative exponent. And so now I'm taking a derivative of a product. So I'll do that first and then go, okay, the constants can be pulled out. And then I would have the first times the derivative of the second. And it takes a couple of steps to get the derivative. But I bring the exponent down, and then I would add 1 to the exponent, and then don't forget the chain rule. So there's the first times the derivative of the second, plus then the second times the derivative of the first, which is a real easy derivative. This derivative of x is 1. Of course, now remember all that is set equal to 0 over here. So maybe just to make my life a little bit easier, I'll just divide by this Coulomb's constant and the charge. Still get 0. Let's get those out of the way. And then go back to positive exponents by bringing this downstairs. So what I'm left with is a negative. This set of 2's cancel off. And I get a negative 3x squared. And then this one, again, if I bring it down, becomes a positive. And if it's not too much to do in one step, I begin to see that if I were to multiply the top and bottom by that same quantity, this denominator would be the same as that denominator. And so now I have a common denominator. And that's, of course, mathematically how you do fractions. You got to get the common denominator. And of course, especially in this case, since our function or our equation equals 0, you could take this common denominator and move it to the other side. And since it's multiplied by 0, you would still get 0. And so now you have just this 3x squared plus the a squared plus the x squared. And then, of course, this x squared and the negative 3x squared makes negative 2x squared, which when brought to the other side is that. And then so finally, when you bring the 2 over and take the square root, Now maybe I'll bring the 2 over and do that. You get 1 over the square root of 2. Did I do that right? Times a.
Yeah.
I don't remember that being the answer. Is that the answer?
Yeah, it is.
It is? Okay. Okay. I'm going to look at the answer. Yeah. Oh, good. Okay. Good. All right. And should I continue on? Because the second part is then what's the value of the electric field? Okay. So you're shaking your head. Yes. Okay. So I'll continue on. And let's see if I can get the camera set here. Because I'll go ahead and I'll just rewrite the equation for the electric field from this ring. It is Coulomb's constant times charge times x over a squared plus x squared to the 3/2 power. And so now that I found it, I'll kind of come back here and show you. Okay, so I found the value of x, so let me put it in. This is the position that it is its maximum. So I'm going to put in a over the square root of 2 for the x there. And downstairs, I'm going to put the x, and I'll just square it, so that'll be an a squared over 2 to the 3/2. Now, if I simplify it a little bit, maybe in the numerator, I'll leave Coulomb's constant, the q, and the a, and I'm going to take this square root of 2 and move it into its denominator out front. And then this crazy thing, I'll factor out an a squared, leaving behind a 1 plus a half. So that's 1 1/2, which I can write as 3 over 2. Did I do that right? For 1, yeah. And of course, all of that's raised to the 3/2 power. Because then I would have, so here's Coulomb's constant, here's Q, here's an A, and this would be the square root of 2. And if you look at this, this is a 3, it's cubed and then the square root. So this is really square root of 3 times square root of 3 times square root of 3. And this downstairs is really square root of 2, square root of 2, square root of 2. And so that square root and that square root go away. That then is a 2 in the denominator of the denominator. Oh, and I apologize back here. This right here is really an a cubed, because this square and the square root would cancel off and you got a cube, and so that a would cancel off with 2 of them. And so it looks like here I got a 3 root 3. And we can change it into a decimal. Maybe I will, but maybe I'll check the answers here. What do they have? Oh,
Yeah,
nice.
the answer is different.
Okay, so good. So I got the same thing, but they went even one step further in the solutions. Okay. They did something that I'm not sure if you saw in the lecture videos yet, because the first chapter is about Coulomb's constants, but later on in history, Gauss discovered, and so the next chapter called Gauss's law, and so you may not have seen this. I don't know where I introduced it to, or I'm not even sure where the book introduces it to you. But Gauss discovers that Coulomb's constant is actually made out of 2 other constants. This first one comes from geometry. And this comes from physics. Let me give you an example. If I think in 2 dimensions and I take a circle, how many radians are in a full circle? 2 pi. This is harder to draw, but if you have a 3-dimensional sphere, and so you're looking not at an angle, but what's called a solid angle, how much solid angles does a sphere have? It's 4 pi. And so when we deal with planar circles, we get a lot of 2 pi's. So like the circumference is 2 pi r. But when we deal with 3-dimensional objects like surface areas, we get our 4 pi's. So maybe I'm getting a little too into math because I don't want to lose the physics here, but I am trying to say here is Gauss is going to take the argument that Coulomb's constant is better written as 2 separate constants. One involving geometry, so there's 4 pi. And this other one he calls the permittivity of free space. And it is equal to 8.85 times 10 to the minus 12.
Got it. Thank you.
And if you put that in, you get the other answer.
Got it.
But I will say, since you asked, and it's a little early, but next week, you'll see me doing a lot less Coulomb's constants and a lot more of the permittivity of free space, because this kind of measures how the electric field moves through space. So this is the physics part of it, and this is the math part of it. And so we will stop thinking about good old Coulomb. We still like him, but we'll just have to get rid of him and use Gauss instead.
So the notation of that is it actually a E0 or it's a symbol that looks like E?
It's supposed to be a Greek letter, epsilon. Would you like me to pull up the book and go to chapter 1 and show you the Greek alphabet?
I'm good. Yeah, I can
so
just write it like E.
It's actually a Greek letter, epsilon, and I don't make my Greek letters. But we don't like to call it an E, because then it sounds like a little Latin alphabet. But as people who are used to Latin letters, all of our Greek letters look a little Latinized.
Okay.
I think it's supposed to look a little more like this.
Oh.
I think is what it looks like.
Yeah, because like I at first when I saw that letter, I thought there's something to do with the constant or the electrical field. So I was confused over there by the answer.
Good. Good. All right, let me check back here in the chat. Anybody shoot me off a question? So I don't see one in the chat. Anybody got anything for me live?
Yeah, could you do number 18 on this 122 homework?
I sure can try. Sounds like it's hard, so I don't know if I can. Just
I think it's very similar to number 16.
Okay. Let me get these out of the way and jump over. We're back to the problem. So 18. So consider an electric dipole. By the way, that's a fancy name that you should probably begin to memorize. If anybody ever says the word dipole, it means you have 2 charges equal in magnitude but opposite in sign. Whereas a bipole, Bi, would be 2 charges of the same charge. So this is a dipole. But they do a good job of explaining, even if you don't know the word. It says, consider electric dipole that's shown in the figure. In fact, as long as I'm sharing the screen here with you, I might even put here chapter 23, number 18. I'll draw a little picture here first. So here's my mathematical Cartesian coordinates. Right here, it looks like they have a negative q on the positive x-axis. And they have a positive q. And they're separated by a distance of 2a. And I haven't read the whole thing, but I think they're trying to say symmetrically. So a on each side. And let me come back and keep reading. So consider an electric dipole as shown in figure 18. Okay, that's got the right one. Show that the electric field at a distance point on the positive x-axis is given by this. Okay. This is a good one. And you said it was like 16. Okay, I'll take your word for it on that one. But this one's got two big steps to it. Let me start with the first step. And that is they're trying to say, what is the electric field somewhere over here on the x-axis, the positive x-axis. And I'll just, in my drawing, draw it kind of far away, okay? Because I think I've only said it once in this Zoom session, but you've got to do these problems by making sure you pay close attention conceptually, and then that conceptual should lead to the mathematics. And so you've got to develop both of those skills. You're shaking your head like, yeah, I get that. So let me start conceptually. Conceptually is this. Conceptually, I'm going to look at this negative charge here and realize that way over here on the x-axis, it would make an electric field pointing towards it, which would be in the negative x direction. Whereas the positive one would make an electric field pointing away from it. And I don't think it's needed for this problem, but the positive one's a little further away, so that's why I'm going to draw the arrowhead a little smaller. And so I can label it. Let me call this electric field number 2 and this electric field number 1. So that when I come down here and follow what I hope I'm starting to get across is that to get the total electric field of whatever configuration you have, a ring, a rod, a disc, 2 points, you need to know what it's made out of. And if you know how to do that electric field, in this case for point, if you add the 2 points, you would get the dipole. And I'll just use this word. If we knew the field from a dipole, we could add 2 dipoles to get a quadrupole. Mm-hmm. Or as we did in example 7 of the book, if we know points, we can add it up and get a ring. And if we know a ring, we can add up a bunch of rings and get a disc. And one of the hardest homework problems is a video answer I already sent out to you. I think it was 28, 26, but it had add up a bunch of discs and get a cylinder. All right. Well, anyway, you're shaking your head. You get the conceptual idea here. So that's the conceptual idea. So coming back to here, I'm going to take 2 points. And it'll be electric field number 1 and electric field number 2. These are each points. These 2 points together is going to give me what I will call the total electric field. And so 2 points added together gives me the dipole. That's kind of the conceptual thing that I'm about to do. All right, so we know how to get the electric field from a single point. So coming back to my picture, number 1, I said was coming from here. And so the electric field from a point would be Coulomb's constant times the charge that's creating it. So that's this negative one.
Yeah.
Divided by the distance away. And let me come back to the picture, because this distance away then would be the position on the x-axis minus a. See, because, X is representing how far from the origin, and this negative charge is A. So down here, I would have X minus A squared. So that would be the magnitude of this electric field. Coming back conceptually, it would be in the negative I hat direction. You good with that?
Yeah.
So on the other one, I would have a Coulomb's constant. I would have a charge Q.
That one's positive though, right?
Very good. It would be X plus A squared. And it would be in the positive I hat direction.
Why is it not X plus 2A because of the positive over
Okay.
2A?
Okay, let's go back to the grid here. What do I mean by X? X is the position on the X axis. X is not the distance from this charge. X is the distance from the origin.
Yeah.
So the distance is X and then an A.
Okay. And then for the negative Q, it's X minus A. I see.
Yeah.
All right. That makes sense.
Right. Now you could have put the origin right here.
And just switched it to 2A, right?
Right. And this would have been an X only.
It's been X, yeah.
And this would have been an X minus 2. Yes.
Right. Okay.
So either one is right. I'm just following their picture. So.
All right.
Okay. So then there's really not a whole lot to be simplified.
Yeah. Would you just simplify it and that would be the answer? This addition?
Except not quite. So let me simplify it and then get to the. That is what I meant by this is the first hard step, and there's another hard step.
Okay.
So I'm going to put the positive one first. It doesn't really matter, but it's just kind of tradition, and I like it to put the positive ones first and then the negative ones. So I would say what I've done right now, if I have solved what you might call the exact equation, this is exactly the electric field. If you told me X was 10 meters and A was 1 centimeter, I can now put those in and find the value of it, okay? But sometimes we have in the physical world situations where A is really small. A good example of this would be, this could be a molecule of water. And so you're talking about this distance being really short compared to here. So we want to know how this molecule of water affects, let's say, some other materials we have. So we could be, quite a bit away on an atomic level compared to the atomic size of the water molecule. So sometimes we do approximations. And so this problem, let me come back here and reading it, says, show that for a distance object X, that's kind of the key. They are telling me, what if X is really big? This X is really big to the A. And if you do that, you can simplify this a little bit. And so you would have an approximate equation, but a very useful equation. So here's what I'm going to do. I'm going to say, do you remember doing things, binomial expansions, such as A plus B squared?
Yeah.
And you get something like A squared plus 2AB.
Yeah, 2AB plus B squared, yeah.
Okay, so this thing's called a binary, and you expanded it with a power of 2. This thing could be a power of 3. And for integers, this is done really well with Pascal's triangle. And let me not do all of Pascal's triangle unless you really want me to.
It's okay.
But I want to get to what's sometimes also referred to as a Taylor series.
Mm-hmm.
that if you take something that looks like this, okay, so there's the binary,
Yep.
but my a is a 1, and my n can be any number. It doesn't have to be just an integer, so that's why you can't do it with Pascal's triangle. You get something that looks like this: 1 plus nx plus n minus 1 x squared over 2 factorial plus n minus 1 n minus 2 x cubed 3 factorial, and continues on.
Yeah.
Okay. Now, obviously, I didn't show this to you, but I will later if you really wanted. But here's the key for this problem: if x is much smaller than 1, for example, let's just say x is about 100. Look what happens here in this expansion. X squared would be super small.
Yeah.
X cubed would even be smaller. X cubed would be 1,000,000.
Mm-hmm.
So what we like to say is you could take something that looks like this and convert it into this, ignore all the other pieces if x is small.
Okay, because
Okay.
I see. I mean, at that point, it's just a not an approximation, but it's insignificant.
Right, yeah, right. That's a good way of saying it. They're insignificant. So let's come back to this problem and see if we have something that looks like this. And we do.
Yeah, because that we're assuming that the x is very large, right?
Yes.
Yeah.
So, so does that mean you want me to continue, or are you good?
Yeah. Keep going, just to.
Okay. Okay.
My.
Right. Okay. So let me do this. Let me factor out an x squared out of each of those terms. So maybe I'll pull this down so you can see it. So I'm taking what we derived, which was the what I'll call the exact equation, and we're going to approximate it. And I would say that the approximation is useful if it gives us a simpler equation and it's close enough, as you said, that the other ones are insignificant. And this does.
Right. Because then you're the 1 minus a squared over x squared. The a squared over x squared is basically 0, right?
What? Okay. Yeah, and actually now that I think about it, I apologize. I didn't even have to make it as complicated as I did.
Oh yeah.
Because I was going to go back to what I was beginning to show you. A lot of these, you want the 1 plus this piece. But if this piece is even smaller, you could drop that one.
Mm-hmm.
And that's what's happening here. And you don't even have to do it. You could just say, this is so small, I can ignore it compared to 1. This is so small, I can ignore it.
But then this just becomes.
Oh, wait. That's my problem. If I ignore those, I get 1 minus 1. I get
1, which is 0, which can't.
Okay. Oh, my bad. Yeah. So I do need to do the next term because the first term cancels off. So the most significant term is the next one.
Right. Yeah, you cancel those out.
Okay, so pretend I didn't scribble that out. Okay, this could be written as 1 plus, and then it's the exponent, so that's a -2. And then the x, which is the a squared over the x squared.
Where's the -2 coming from?
The power it's raised to, come back here.
Oh, I see. Yeah. Yeah, and nx, right. I just right. Okay.
Like I made a mistake somewhere. Oh, shoot. I did. Let me backtrack. I don't know why I put a square here. I think because in a earlier problem, we had that.
Yeah.
So let me come back to here. See, when I factor out an x,
You don't get.
there would be no square there. So this should have just been a over x and then an a over x.
Yeah.
You got that? I apologize. Okay. Okay, and then doing the same logic to this one, it's 1 minus, and again, this would be a -2 up here. So this would be 1 minus from that minus, and then the power it's raised to, which is the -2, and then an a over an x.
And then combining those is what gets you the x cubed on the bottom.
Yeah, so Coulomb's constant times q over x squared I'll leave alone. And then you can see here that the ones cancel off, so that's 0. And then this is a -2. And this is a little hard to see, but it's also a -2 because it's a negative, a negative, and a negative. And so these are actually both -2s. When I put them together,
You get -4.
-4. X over A. I'll put the -4 in front. Coulomb's constant, a Q, an A, and then an X cubed. And let me just look at the answer, and they got a -4QKA X cubed. Yeah, good. So that was what I meant by the second half of this. This is a hard second half.
Okay. Yeah, I was getting lost in the math. I got E total equals the negative Coulomb's constant Q over x minus a squared in the other term, but I just couldn't simplify it.
Nice.
Okay.
So, and I'll give you a little hint. There's probably about 3 or 4 problems throughout the chapter that make you do this expansion, the binomial expansion. And if you want more, look at Appendix B of the survey book. I think I mentioned all of this in one of the answer videos. You may not have got a chance to see it, but they show up a lot. Your author also did it in the reading, but it is probably very new to you because we didn't do things like this in 121 or in 123, but in 121. So this always catches people off guard, this first chapter.
Yeah.
I've already got a lot of email questions on it, and I'm all,
The math is very foreign right now.
Yeah. So one thing good and bad about this class is you'll pick up your math. You'll have to do a lot of either relearning or maybe even learning for the first time of your math. Like, oh, how do I do integrals? Oh, how do I do derivatives? Oh, how do I maximize? Oh, how do I do a binomial expansion? Oh, how do I do cosine? How do I integrate by parts? So I looked here at the time. We started at 12:30, right?
Yeah.
So our break is at 2. Sounds like you guys have some more questions.
Yeah.
I'm mentally tired, so I would probably just come back at 3.
Yeah, that's what kind of I'm thinking. Why don't we take our break and come back at 3, and then we'll be here
Okay.
from 3 to 4:30 again.
Okay.
Thanks.
Quick question before
Yeah.
you do leave, though. When you grade the homework, do you grade for completeness or?
No, yeah, not the homework. The homework is graded for trial and effort, and so you should be getting 100 on it if you're putting in the real effort. The answers won't be checked. No,
Okay.
I'll check the answers on the test, of course.
Yeah.
But on the homework, it's part of the learning process. So right or wrong, you get credit for it.
Because there was a problem earlier in the homework where I got something close, but I couldn't pull out the exact numbers you got in the solution. So
Right.
I just left it as my solution. But yeah.
Yeah, and that's fine. It might serve you well though to figure out why yours differed a little bit. If it's just rounding, oh, no big deal, because I'll see that when I'm grading the test. If it is just in a different format, that's not a big deal either, because I would see that during a test. But it might be nice for you to convince yourself that it is the same format, and so that
Yeah.
exercise of saying, hey, those are really equivalent is actually good for you.
Mhm.
Right.
Yeah.
Do you, when you grade the exams, if we do like 90% of the problem correctly and then mess up right at the end, do we get the partial credit? Is there a significant portion of partial credit?
Yeah. If you talk to any of my old students, I give a lot of partial credit. I always look at logic. In fact, the harder ones for me to grade are the ones that the student makes just a small mistake at the beginning, but everything else is logically sound from there on out. It looks totally wrong, but it is actually really good. So I give like
So they
90, 95%.
follow the train all the way down properly, but
Yeah.
sometimes
So I'll be checking for your thought process. So if you just started with some kind of weird thought at the beginning, you'll probably get 90% of it right, even though it looks totally wrong.
Yeah. So essentially, just write everything you do down.
Definitely.
And you're likely to get good points.
I'm trying to see your thoughts, and I read a lot more into it than maybe I should, but I think you guys are deserving of that. And I'm convinced that students do have a lot more understanding than sometimes the final answer indicates.
Mm-hmm.
And so, you'll see my former students, they always say, oh, good thing for partial credit. It got me through the class, because I never got one completely right, but the thought was there.
Right.
Yeah, that happened to me in Physics 121, where I got like the main idea, but like the first test, I didn't get any of the problems 100% right, but I got like 7 out of 10 or 8 out of 10 points. So
Yeah, that's what happens, and that's what I'll be looking for, because that's common. That's part of the learning process,
Mhm.
yeah.
Okay. Well, thanks, Dr. Young. I might be back
All right.
for your last session. Also, I wanted to compliment the way that you do labs in the
Oh,
offline.
thank you.
It's very good.
Yeah.
Oh, good. Thanks for the feedback. Yeah, it's the only one I've done, so I'm learning too.
Yeah, I really like the way you did it too, because I took Chemistry 101 over summer.
Oh, you did? Okay.
And the way she did, like the way that teacher did labs, it was just a nightmare, and like it was kind of just not really. It wasn't good for students, I'd say.
Okay.
Yeah,
Well-
but I really like how you did your lab too.
Good. I appreciate that. The labs are designed. Of course, I've never done remote, but in a face-to-face setting, the idea is it should complement your learning. What are you learning in class? And so, and back to your earlier question, Daniel, that those labs too will be graded on effort, not for completeness. So again, it's part of the learning process. Yeah.
Okay, cool.
All right.
Well,
All right, guys.
I'll see you in a bit.
Okay. Bye now.